Welcome back. Last time, just to keep track of where we've been and where we are going, last time we covered weathering, physical weathering, chemical weathering, and then we thought about our soil forming processes, the actual things happening within the soil to create the horizons that we see. And we looked again at our horizons and added some detail. Looked at several subordinate designations, the little letters that tell us what kind of A, what kind of B, what kind of C horizon do we have. It wasn't an exhaustive list. I'll save that for soil morphology. SS 321, there's more than a full alphabet worth of letters we could put on there, but I gave you some key ones. So if those sound familiar, great. If you're a little fuzzy on those still, then maybe go back and take another look and make sure you are comfortable with where we have been. Today, we are going to be talking about soil forming factors. I mentioned this is different than the processes. Processes are the things happening. The factors are the agents causing the changes, the things doing stuff to the soil, acting on the soil. And there are 5 of these. Today we're going to hit 2. The next 3 we're going to save for next week. So I know you'll be waiting with bated anticipation for the final 3 factors, but we're going to look today at parent material and climate as factors in soil formation. This is an equation that was kind of first put, at least in this format, by Hans Jenny, who was a soil scientist at UC Berkeley, and he came up with this concept in the 1940s, and it was sort of putting into equation form, basically, some ideas that were out there, but he kind of really pulled it together in kind of an elegant way. So this equation, S, is for soil. And so soil is a function of these elements, these factors. Climate is the CL. O is for organisms. R, relief. P is for parent material, and T is for time. I showed you this list once before in week 1, so hopefully somewhere in the back of your mind you think, oh yeah, that sounds familiar. We often call this CLORPT. And if you just remember CLORPT, you've got the 5, you just have to keep a couple things straight. P is parent material, it's not precipitation. T is time, not temperature. So you have to remember what the letters stand for, but that CLORPT idea, that CLORPT word, will give you these 5 factors. And in some combination, looking at those 5 factors, figuring out how they're interacting with each other and all acting on a soil body, you should be able to predict any soil on Earth. We can't do this. Computer programming, modeling, we can't actually solve this equation. It's just way too complex. Given all of the changes that happen, like T for time, well, climate is not steady. It's not like we've had the same climate for the last 100,000 years. And so you have to know all of the details, and we just don't. It gets very complicated, but it helps us kind of frame the question. How does this soil form? Well, it's a function of these 5 factors. And we will start our discussion with the P for parent material. And that's because it kind of connects a little more to some of the things that we've been talking about, and it's going to be relevant for your lab activity, your assignment this week connects to some of that parent material. So I'm going to there first, and then we'll jump around just a little bit. But parent material to kick things off. And parent material can be divided into a couple different groups. We're going to start with the residual parent material. Residual means residue. It's just what's left behind when you form a soil in place. We're going to contrast this with transported materials. This is not transported, it's just we start with a rock and it breaks down. So this hasn't traveled anywhere, it's just in place, weathering of a rock. Rocks, a little refresher from kindergarten potentially. You've probably heard about these groups a few times in your life. Igneous, sedimentary, and metamorphic. Hopefully those sound a little familiar. We'll do a quick refresher and give some details here. Rocks are made of minerals, and you're going to be looking at some minerals in your assignment this week. This is a partial list. These are primary minerals. Primary minerals means these are ones common in rocks. Crystalline rocks. You get a hunk of granite, you're going to have things like quartz and feldspars and micas. They're formed through rock formation, not soil formation, but rock formation. So cooling of magma produces minerals like these. Some key ones: quartz, SiO2. You should be familiar with quartz. It's a very common mineral. It's hard, it weathers slowly. You get a lot of sands from it because it is resistant to weathering. A couple others that are important: the feldspars. And orthoclase and plagioclase are examples of feldspars. There are a couple others and some different names that get thrown around. Plagioclase is a group. We're keeping it at the surface level here, but feldspars are somewhat hard, but they weather a little faster than quartz, and they're also extremely common. They're all over the place, and they produce clay. So important for that reason. We mentioned that last time. Micas, again, here's a group, and muscovite and biotite are some examples of micas. Those ones are pretty common, things you've probably seen before. Some others, dark minerals. I mean, we're simplifying things here, right? But augite and hornblende are a couple examples. And then we've got in this last box some less resistant calcite, dolomite, and gypsum. These ones are somewhat soluble. You can find them in your primary rocks, but they also will form in the soil. So an important group of minerals and important in soils. If we look at our secondary minerals, so primary, that's what makes up your starting rock. Secondary is what forms after weathering has taken place. So gypsum, as I mentioned last time, it can be primary, but you can also form this one from weathering. If you have a rock with some sulfates or some calcium, or one of those two and the other comes in through water, you can produce gypsum. Calcite and dolomite are carbonates. We talked a little about carbonation reactions and dissolution of carbonates. Clay minerals. Soils are clay factories, and there are a lot of different clay minerals, and we're going to get into details later this quarter, and that's great fun. I love soil minerals, clay minerals. We're going to leave them as a nondescript group for now, but very important in soils. Iron and aluminum oxides. Again, that's the category, and hematite and gibbsite are some examples. And again, quartz, found as a primary mineral, but you can also produce it from weathering. So those are some groups of minerals. I want to make a point here. We're going to talk about plant nutrition and soil interactions later in the quarter. But for now, I'm just throwing this out here, and I think it'll come up again in your assignment a little bit. There are 17 essential nutrients that all plants need to complete their life cycle. They are essential because they can't live without them. This little mnemonic, C. Hopkins Cafe, mighty good. Cousin Mo cleans nicely by midnight. I've bolded the chemical symbols for each of the 17 nutrients here. So we've got carbon, hydrogen, oxygen, etc. Nickel, Mn for manganese, Mg for magnesium. So 17 essential nutrients. If you look at that list, the first three, CHO, those mainly come from water and air. We've got CO2 and H2O. Those are sources for those elements for plant growth. But everything else, the other 14, primary source is soil minerals. Some of them, a lot of them get recycled through plant death, decay, decomposition, nutrient cycling. Some of them, nitrogen, that one can come from minerals, but probably more commonly from the atmosphere. So there are a few other things, details that we will expand on as the quarter progresses. But minerals are important. One reason is they are the ultimate source of many of the essential nutrients for plants. So minerals make rocks. For rocks, I said there were three groups: igneous, metamorphic, sedimentary. For now, we're going to think about igneous and metamorphic rocks as similar. They are crystalline rocks, and so we're not going to talk a lot about the metamorphic, but they have a lot in common in many cases with our igneous rocks. So we're going to focus on igneous rocks. And for our crystalline igneous rocks, we group them by these two axes, by composition. So sialic rocks have a lot of silicon and aluminum. Quartz is dominant in sialic rocks. Mafic rocks have a lot of magnesium and iron. There are different terms that get applied to those, but I like those because they help you remember the specific elements that are common. And mafic rocks are lower in quartz. Quartz is silicon dioxide, SiO2, less silica, so less quartz in our mafic rocks. And then we've got sort of intermediate in between. That's one way we group them. The other way we group our rocks is by grain size, and that is going to be either coarse, big grains, or fine, small grains. The way we get coarse grains is cool slowly. That gives elements time to get organized and build bigger crystals. If you cool very rapidly, you get very small crystals. And then, depending on where you fall on this table, if you're coarse and sialic, that is where you get granite. If you're coarse and mafic, you get gabbro. Coarse and intermediate is diorite. Fine grain, sialic is rhyolite, mafic is basalt, and intermediate andesite. So those are good names to be familiar with. Kind of the main representatives of our crystalline rocks. You can also have ultramafic, so these are really low in silica and really high in magnesium and iron. Things like peridotite, serpentinite, that one metamorphic, but a common ultramafic in composition rock in this area, or in the Central Coast. So there are some pictures to kind of give you the visual here. And you can see our coarse rocks up on top. You can make out, they kind of look splotchy because they've got larger crystals. This is on the fine end, of course. The one in the middle here is a little coarser. Down on the bottom, the matrix on these rocks is pretty fine. You can't make out much splotchiness on those. This one has some splotches. Those are actually inclusions of larger crystals, so it gets a little more complicated, but you can kind of see the range here. You'll also notice mafic rocks tend to be dark in color, and sialic rocks light in color. And this is kind of the province of igneous rock formation, melting and cooling, below ground, slow cooling, big crystals, above ground, faster cooling, and smaller crystals. So that takes care of our igneous and our metamorphic. We're just sort of take rocks and minerals with me, and we'll spend a lot more time on it, don't worry. But for the sake of moving things along, those are our crystalline rocks. The other group are the sedimentary rocks, and they're actually, in terms of what's under soils, 2/3 of all soils are under sedimentary rocks. Sedimentary rocks have gone through the rock cycle. They're broken down pieces of other rocks that get transported, deposited, lithified, turned into a rock. And so you've got sandstones and shales listed on this slide here. Limestones, dolostones. They're composed of fragments of other rocks, or in some cases like limestones, shell fragments, but other things, sediment, that gets deposited and lithified. They've often been weathered once or twice or 3 times before, so they've been processed a little more than the crystalline rocks. And if you form a soil from residuum in place from rocks like these, the soil that forms is going to depend a lot on the properties of the rock you're forming from. If you're forming from a sandstone, you'll probably have sandy soil. If you form from basalt, which weathers relatively easily, it doesn't have a lot of the resistant quartz, so it breaks down relatively easily, and it's got fine grains, which means lots of surface area to break down, then you're going to weather a lot faster in basalt than, say, in a granite that has coarser grains, so less surface area on individual grains, plus a lot more quartz, which is very resistant. It's going to be slower weathering. So it's going to depend a lot on the rock you're forming from, In general, though, it's a relatively slow process. Going from a hard rock into a soil takes some time. So here's kind of a summary slide. Residuum, it's not transported. It forms in place. The sorting of by particle size, that means, are all of this grains similar in size, or do you have a wide range? And in residuum, you often have a wide range. It depends a little on what you start with, but you can have big stuff and fine stuff all weathering out of the same rock. And the characteristics depend on what are you starting with. Next option is transported. So residual, non-transported. Transported is transported. And this is sort of the precursor to sedimentary rocks. We're in that realm where we've broken down the rocks, or we've weathered eroded soil, we're carrying sediment, we move it somewhere and drop it, and then we form a soil. What our transporting agent is determines what kind of transported material we're dealing with, and they have some distinct properties. So first up, alluvium is deposited by running water. So some examples: floodplains and terraces, alluvial fans, deltas. I'll show you some pictures here. So here's a cartoon of a floodplain and a photo of a floodplain. And the rule of thumb with alluvium is where the water moves fast, the particles, the grains, are bigger. In the channel down here, we're going to expect some pretty coarse grains, right? High energy, it's moving big stuff. All of the small stuff is getting carried away, and so only coarser material gets deposited. When you go over the levee onto the floodplain, it's going to be finer, but you're going to start out with sandier stuff on the edge, and as you move away from the channel, out in this region called the distal part of the floodplain, distant from the source, it's going to be finer. So you'd expect fining away from the channel. You'll notice there's a little scarp here, right? A rise, and then we've got another surface up here. This is a stream terrace. And there's another rise, and here's another stream terrace. And each of those are former floodplains that have been uplifted. They're no longer getting flooded. And so we'd expect similar patterns, but this is going to be young, and this is going to be medium in age, and this is going to be old. And so you'd expect more development depending on which terrace you're on. A couple other alluvial features: alluvial fans, more common in more arid environments and areas with steep topography. And these fans have been outlined on this drawing. As you come out of these canyons, high energy water suddenly slows down when it hits the valley, and it drops the sediment that it's carrying. Again, this is the close to the source, so you would expect coarse sediments. This is the proximal part of the fan, and down here at the edge, on the distal part of the fan, distant from the source, you'd expect finer material. Doesn't mean it's pure clay necessarily. I mean, there's still a lot of energy at the base of a fan, but we have that trend, fining away from the source. This is a delta down here, and at a delta, that's where the water from a river is entering a larger body of water, a lake or ocean, and the water basically comes to a stop. So anything that the water was carrying falls out because things have slowed down to almost not moving at all. Very fine sediment can fall out. So in deltas, we expect clays and fine silts, very fine sediments. With alluvium, there are a couple things we expect. One, illustrated in this photo that maybe you've seen before. With frequent flooding, we get stratification. So layers, little deposits stacking up from that. And sometimes we get buried material if the floodplain shifts, or something was out of the floodplain for a while and the stream channel shifts, you can bury stuff. So those are somewhat common features in floodplains and alluvial systems. Another point here, and it's not very, I was hoping it would be a little bit illustrated, but alluvium, water tends to round particles. So when you get gravels and large sand grains, they look nicely rounded because they get tumbled around by that running water. So alluvium, Flowing water, it's good at sorting particles. High sorting, so you get a lot of sand in one spot, you get a lot of silt in another, a lot of clay in another. They get separated out, so good sorting. And they tend to be relatively level surfaces, especially on floodplains and fairly fertile soils. You've probably heard about the Nile flooding regularly and getting replenished for ancient Egyptians to plant their crops. And that's based on this refreshing of new material from the alluvium. Other modes of transport, lacustrine deposits. We're not going to get into the details today, but you can also have deposits in a lake. It's not running water. It's almost still water, so you would expect very slow deposition, very fine material in a lake bottom. Glacial deposits, we will look at just a little more. They're not hugely important in the Central Coast, but nationally and globally, they have produced some pretty important soils. So with glacial, there are two subcategories here, till and outwash, that we'll look at on these images. Glacial till is the stuff that the ice is picking up and grinding and carrying with it. It's just a total hodgepodge of whatever the ice is flowing over. With glaciers, you're maybe familiar with mountain glaciers that are running through little canyons, and they do this, but where it ends up being more influential is Ice Age type glaciers, the kind that we don't have expanding in North America anymore, but some of these continent-sized ice sheets pushed their way across the Great Plains and just picked up everything in their path and carried it in that ice. Just big stuff, little stuff, doesn't matter, the ice could pick it up and carry it. When the ice melts, all of that stuff just basically falls in place, and you get glacial till. So this really poorly sorted, random mix of material. So being carried in the ice up here, and you can see it in this image, coarse stuff, fine stuff is just a jumble. Some of it's rounded, some of it's angular, it's everything that the ice picked up. It's level, because where the ice traveled, it flattened everything, but then it's just jumbled. Glacial outwash is featured in the lower part of this, and glacial outwash is at the end of the glacier. As it melts, that produces a lot of water, and that water basically becomes rivers, right? And you get floodplains and deltas at the end of the glacier, and so those are basically alluvial features, but we happen to know that they were associated with the melting of a glacier. We call those glacial outwash. So looks a lot like alluvium because it basically is, it just happens to be sourced from the glacier connected to that ice. And so in this case, this is outwash underneath the till. That tells me that this is probably older from a previous glacier. We were off the edge of the glacier and had melt depositing this stuff. You can see the stratification that reminds you of the alluvium we looked at. And then a new glacier came on top of that old outwash, and the till was deposited on it. There are other features, things like moraines are associated with the edges of glaciers, and they're basically composed of till but have some specific topographies to them. In terms of the properties, they look like glacial till. So glacial till, transported by ice, it has low sorting. It's got very fine stuff, the rocks that get kind of powdered and ground up. It's called glacial flour. It's very silty, but it goes all the way up to boulders being carried by the ice. And I think you can read the other points there, but we've basically covered the concept of this glacial material. Next agent of transport is wind. And if you have wind blowing stuff around, those are called aeolian deposits. And wind can blow up to sand. It can't blow around anything much larger than sand. And even sand, it can pick up and move a little bit, but it doesn't carry it long distances. So most of our aeolian deposits tend to be sand-sized or silt-sized. L-O-E-S-S here, that's loess. And loess is silt-sized. Make that clear here. Clay can also be carried by wind, but because it's so small and low mass because of its size, it gets dispersed a lot more, and you don't tend to get thick deposits of clay from wind transport. The other wind transported material is volcanic ash, and that's, you don't have to have a whole lot of wind, you have to have the volcanic eruption, and so it's sort of a unique group. We're not going to talk about it a whole lot right now, but volcanic ash is a unique parent material with some interesting properties that we'll discuss a little more probably next week. So here's an example of some loess areas. The way we get loess, so it's these thick deposits of silt, and the most common way that loess is produced is you start with a glacier. So going back to our glacial material, we have the glacial ice sheet. Continental glaciers move across the Great Plains and just flatten them. And then they recede, and what they leave behind is this till that's got big stuff, but also the fine stuff, the glacial flour. And you've got these vast open areas that wind starts blowing across. It's uninterrupted. It can just pick up and blow like crazy through there. I've been to Kansas for 1 week, and it was windy the entire time, and people who lived there said, oh yeah, this is typical. 20 miles per hour is just kind of your baseline, and it goes up from there. So lots of wind in these vast open plains blowing across the till. They pick up what they can, which is the silt-sized stuff. Medium, it's small, but not tiny small. Picks it up, and then once it hits something that slows the wind down, some hills or a little bit of topography, the moraines, they may not be big enough in most cases to slow the wind down too much, but you hit mountains or something, the winds slow down, and the silt falls out because the wind has slowed, and you get these thick deposits of loess. In the Midwest, they can be many, many feet thick. The Palouse Hills, it's a smaller area, but similar processes, and you just get this thick, silty material that's very fertile, holds a lot of water, but it's not too sticky like clay can be. We'll talk about physical properties later, but tends to be very productive for agriculture. Sand, windblown sand, generally forms dunes. They're much smaller in geographic extent. The sand can't travel too far, but you can get these very well sorted. All of the finer stuff is blown out, and all of the sand kind of gets piled up together. So, image on the left, this is in dune sand. This is forming in loess, a soil forming in aeolian deposits. Wind is really good at sorting material. It is even better than water, so you get just almost straight silt or straight sand, and not much else in it. Depending on what kind of material, the loess is fertile. Dune sand, not so much. There's not a lot of nutrition held by sand. One more transporting agent is gravity. And material transported by gravity we call colluvium. So gravity doesn't move things very far. It moves it from the top of the hill to the bottom. And if you've got a big hill, then that can be kind of far, but you're not thinking miles, you're thinking maybe hundreds of feet. It also doesn't have, it's not a constant flow, right? Gravity, you get a landslide, you get an earthquake and things shake loose and slide down the hill, and it's a one-time event. There's not time for mixing and sorting and processing, or nothing can really happen during that time other than relocation and mixing. And so for colluvium, we expect a jumble of material. Whatever was on top of the hill ends up at the bottom, but totally mixed. So colluvium, very poor sorting, and its properties are just totally dependent on what was higher up on the hill. Often it's rocky, because hills are also often associated with underlying geologic features, but there's not a whole lot you can say consistently other than whatever was at the top of the hill, mix it up and put it at the bottom. In San Luis Obispo County, colluvium is all over the place on all our hills. Things are moving downhill and jumbling things up a little bit. So we've covered residual material, we've covered transported material. The last is organic material. So all of that we've been talking about is inorganic, bits of rock and sediment that's moved around. The other option, totally different realm of thought, but also important in soils, is organic accumulation, organic parent material. So places where you get a lot of organic material building up are places that are flooded. The water keeps the oxygen out, which slows down microbial decomposition, which means the organic material can start to accumulate. And in a swamp or bog or wetland, you can get thick organic deposits. Here's an example of a organic soil, all of this material up here. This is a former lake bed that the lake kind of got filled in with plants that gradually died and settled in the bottom of the lake and filled it up. Down below we've got some chalky material from lacustrine deposits, but then we've just got decomposed plant material sitting on top of that. If you were to burn this material, it would just all burn away. We don't have sand or silt or clay in there, it's just organic. Another name for that is cumulose. It's accumulating in place. Different than residuum, the stuff that's left over as you break down rocks. We're actually adding new material and accumulating. It's not transported. I mean, you could in theory move this stuff around, but as a rule of thumb, mostly it's just stacking up in place. And you might have some mineral stuff mixed in a little bit depending on your setting, but dominantly in areas with water saturation protecting it. It also, if you're in a frozen environment, that can also help protect it a little bit. So they are very fertile if you drain them. Otherwise, they're a little wet to grow a plant. But all of that organic material, lots of nutrients. But once you do drain it, they become very fragile. Well, we'll talk about that a little more going forward in the quarter. So, this is long enough on the video. I'm not going to dwell on these questions, but again, going to include them in the slides and let you take a look at them here. Pause, try and answer them. If you can't come up with an answer, consult with one of your classmates. Come to office hours. Make sure you are comfortable answering some of these questions about parent material. And one last note, sometimes students say, why did you change the color of the border on your slides? What does that mean? And the answer is it doesn't actually mean much here. It's just sometimes I find that if I'm trying to remember, wait, what lecture was that in? If I imagine a slide, I'll also see the color that appeared with it, and then I can go find it a little more easily. So it doesn't mean anything. It's just to sort of change the look just a little so that when you're going back to study for the midterm, maybe you'll think, oh yeah, that was in the yellow slides. So that's all that means. All right, those are a few review questions for you to take a look at. Let me know if you can't figure out an answer. But between your book, the material I've covered, and your classmates, hopefully you can figure out each of these. And I like parent material, so I've given you a lot of questions here, but hopefully those are helpful. I will leave it at that, and we will pick up with climate as our next factor of soil formation in the next video.